Good morning, students. So today we will start our discussion where we have left in our last class. We have already discussed the solution of simple harmonic motion equation, and we have found the general solution for that equation. X is equal to a sine omega t plus phi, and we have seen the expressions for velocity and acceleration. Today in our discussion we will start with the energy part, kinetic energy of the particle and potential energy of the particle in SHM, and we will see the average energy and other things accordingly. Let us see if you are seeing my screen. I hope you are able to see the screen. So we are into the part third of module 2, oscillations, in which we are discussing simple harmonic motion. These are the parts of the module 2, and we are into the simple harmonic motion part. Then we move to damped and other thing. But this is the third part of SHM. And myself, Dr. Pradeep Sharma from University of Engineering and Management, Jaipur. You can note down my contact number and email ID in case you require to report any problem or you want to discuss any doubt what we are discussing. If you have any problem or doubt in that, so you can write to me or you can WhatsApp me on this number. So in module 2 we will be discussing all these parts, and we have just started with simple harmonic motion, that is under this free vibration part. So all these parts we will discuss accordingly after having an idea how the simple harmonic motion takes place and how the total energy of the harmonic oscillator is. So till this point, I hope you have understood what a simple harmonic motion is, and if any simple pendulum or a mass attached to a bob, a mass attached to a spring are taking such motion that acceleration is proportional to displacement, and there is a force always working towards that the particle remains or returns to its original position, that is restoring force is available in that system. So that motion can be in simple harmonic motion. Today we are going to describe the total energy of this type of oscillator, and first of all we will see the kinetic energy. We know that kinetic energy is actually responsible for the movement of the particle, and it depends on the velocity also. So k is equal to half mv square, but the expression of the v in terms of simple harmonic motion we can easily find out by this dx by dt, where x we have. So this is the part for the kinetic energy, and the potential energy, which actually depends on the position of the particle at any moment. So that we can find out like as dot dx integral, and 0 to x, if we can integrate it, the force is kx, the restoring force, and half kx square. And the value of x is again we can put for here. And k is n omega square, so we can make out that this part is available. So you can see that the kinetic energy we have received in cos square part, and the potential energy we received in sine square part. And you can make out that if we sum up, because this is also half m omega square a square, this is also half m omega square a square, so this will be coming out when we will be finding the total energy of the system. So you can make out that the cos square plus sine square is 1. So total energy is half m omega square a square. So this is the total energy of the oscillator. You can see here. Suppose here this is the mean position, and it is moving like here and there in negative direction and in positive direction. So if you see over here minus xm, so at this point, so you can understand that where the kinetic energy is maximum and where it is minimum. So where the velocity is maximum at the mean position here. So that's why the kinetic energy is maximum here, and the potential energy is minimum. And at the extreme point, velocity is negligible. That's why kinetic energy is minimum, and at those points, extreme those points, potential energy is maximum. So I hope you can understand by seeing this diagram how the kinetic energy and potential energy concept is working. So this we can make from this demonstration. Okay, so it can be any oscillator, it can be a pendulum also, or it can be a mass attached to a spring. There can be a mass attached to a string also, and it can be suspended with a related support. So we will have the same notation for kinetic energy and potential energy. If you see the average energy of this oscillator, here you are seeing that these two graphs are basically opposite to each other. So what can be the average energy at any moment? So if we try to see that, the average potential energy for one complete cycle is given by this symbol, and 1 by t, because it's a complete cycle, integral 0 to t half kx square dt. So this is in reference to the time, and this value we can put 1 by t 0 to t half k x square dt. This is the value of x square. You can solve this integral. This comes out to be 1 by 4 m omega square a square. So this is the potential energy expression. This is the average one, because you know that integral 0 to t sin x square omega t plus phi dt by capital T is, so this expression you can use. Then potential energy is half 1 by 4 Ka square. This is the average potential energy. Now for kinetic energy is again for the complete cycle 1 by t 0 to t half m velocity square. The velocity is dx by dt, velocity square. So we can put the value of this velocity part dx by dt in terms a square cos square omega t plus phi, and we can solve again. The value will be 1 by 4 m omega square a square, and again 1 by t integral 0 to capital T cos square omega t plus phi dt is half. So we can use this value to find the average kinetic energy. So average kinetic energy is 1 by 4 Ka square. So if you see the expression for average kinetic energy or average potential energy, you can make out that these two are equal and equal to 1 by 4 Ka square. So this is constant. So at any moment of time, the average energy of the simple harmonic motion taking object is constant. And total average energy over a complete cycle, if we say the kinetic energy plus potential energy, so we sum up, so that will be half Ka square. This is the total energy. So it is evident that total average energy over complete cycle is equal to the total energy of the harmonic. So this is the energy conservation law in simple harmonic motion. So this is in compliance with that. So it means that at any moment, the average energy, average total energy at any moment in simple harmonic motion, it will be equal to the total energy of the system. Now we are going to learn a very important part, because when simple harmonic waves or any wave right now will move in any direction, so we are going to learn the superposition of waves that will lead to actually Lissajous figures. What are Lissajous figures and where we can use it, and what are its applications, we will try to understand. So principle of superposition is stated like, if the two waves, if the wave equation of SHM are linear, then the resultant displacement at any particular instant is algebraic sum of the individual displacements due to different waves. It means if there are two mutually perpendicular SHMs we are taking care of, then the resultant displacement will be the sum of individual displacements. Suppose one wave is moving in x direction and another wave is moving in y direction. So from x is equal to a sine omega t, we can make out this sine omega t as this, and from y is equal to b sine omega t plus phi, because these two waves will have some phase difference. So sine omega t plus phi is equal to y by b. Now we can open this with formula, the trigonometrical formula, sine omega t cos phi plus cos omega t sine. We'll put the values accordingly. We'll solve it. We'll put for cos omega t as under root 1 minus sine square omega t, and this way. We'll solve it and we'll find that we'll get this equation: x square by a square plus y square by b square minus 2xy by ab cos phi is equal to sine square phi. This is a general equation of ellipse. So we can say that if two waves are there, one is moving in x direction and another is moving in y direction, then due to those superposition of those two waves, like here, the resultant will be an ellipse. We have to see the special cases when phi is equal to 0 and sine phi is 0 and cos phi is 1. So it reduces to this equation x square by a square plus y square by b square minus bxy by ab, which is the whole square of x by a minus y by b. So y is equal to b by ax. This is the displacement equation in y direction we got. So if you see this, this is kind of y is equal to mx plus c, where c is 0 and m is b by a, m is the slope. So it is actually the line passing through the origin, making an angle theta, then inverse b by a with x-axis. So in the positive direction, this will be there. Suppose this is the origin. So this line will pass through the origin and we'll have some angle with x-axis. The angle is theta is equal to tan inverse b by a. Now if we see and try to change the value phi is equal to pi, then two SHMs are in opposite phase. So sin phi is 0 and cos phi is minus 1. So in that case, it will reduce to y is equal to minus b by ax. So if you see 1 by 1 step, it is y is equal to minus b by a. So slope is reversed. So when the slope is reversed, so it is again passing through the origin, but it is lying in second and fourth quadrant, and angle theta is tan inverse b by a, and we see that this is the change. So now this angle is here with x-axis. Okay, so direction of this is reversed. This line is, the slope is reversed, minus b by a. So in this way, different type of shapes we can analyze using the superposition principle of two waves. But the third condition is very important, because we can see that when phi is pi by 2, so we can see sin phi is 1 and cos phi is 0. So in that case, it reduces to a circle. X square by a square plus y square by b square is 1. So this is an ellipse. But if we take that a is equal to b, then it will be a circle. But right now it will be an ellipse having major and minor axes as a and b. But in this condition, when the initial amplitudes are equal, so it will reduce to an ellipse. And in that case, we will find this ellipse on the screen. So starting from a positive slope line, then a negative slope line, and because the line is a case of ellipse also, line is a special case of ellipse. So it reduces to ellipse actually when phi is equal to pi by 2. And if the amplitudes are equal, then that ellipse reduces to a circle. So 5 by 4 or 7 pi by 4 or so on, so resultant will represent an oblique ellipse. So accordingly, we can see that oblique ellipse is also possible in this case. And this Lissajous figures, we can define that when these two simple harmonic motion superimpose to form various type of figures and shapes, which depends on difference of phase between them, what exactly we have seen already, then these figures or shapes are called Lissajous figures. So in the last, these diagrams we have seen that these are actually the Lissajous figures, because these are generated due to the superposition of simple harmonic motions, and there is a relation of their phases, and accordingly we can find the values. So Lissajous figures are helpful to find the ratio of time periods or ratio of frequencies of SHMs, This is the main use of Lissajous figures. We can find the ratio of time periods or ratio of frequencies of two SHMs. And it also helps to find the frequency of tuning fork by finding the ratio of frequencies. And it also helps to find the nature, shape and amplitude of signal waves. So this is the most important part. So if any signal wave is available, so actually Lissajous figures help us to find the nature, shape and amplitude of those signal waves. So these are important applications of Lissajous figures. So in this way, we have discussed the production of Lissajous figures, the superposition of two simple harmonic motion waves, and then we can see how it is taken care and where it can be applied. So for further discussions, we will meet in our next meeting. Thank you. Thank you.